Welcome back, my friends, to the show that never ends. We're so glad you could attend. Come inside, come inside. There behind the glass stands a real blade of grass. Be careful as you pass. Move along, move along. Come inside, the show's about to start. Guaranteed to...
Hello, I'm Brad Kubin, Editorial Director of MetalForming Magazine at the Precision Metal Forming Association, and I'm pleased to once again welcome you to another edition of MetalForming Live, our ongoing webcast panel discussions. Today, we're presenting the first of three in our summer series, with today's session focused on in-die technologies that promise to eliminate downstream operations in your press room. As metal formers and stampers continue to seek ways to become more efficient, as well as ways to value add and increase profitability, in-die technologies allow them to achieve both time and cost savings and to add value to the products that they manufacture. So we've again put together an excellent group of panelists for our session today, all with expertise in developing in-die technologies and in applying those technologies in the press room. So our senior editor, Kate Bachman, is going to moderate this session for us today. And myself and senior editor Lou Kren are also online, and we'll pitch in as needed. Before I turn things over to Kate, I'd first like to thank our sponsor for the session today, Wilson Tool, for its generous support of the MetalForming Live series. And as always, I'd like to remind all of you joining us online, as I do before every session, that these events are really meant to be interactive and dynamic. We want you to ask questions of our panelists, so please use this opportunity to learn more about in-die technologies and how they're used. Please participate as you would if you were here with us in the room, and use that Q&A panel on your Zoom screen to ask questions of our panelists throughout the session. All right, so without further ado, Kate, take it away.
Thank you, Brad. And thank all of you for joining us today. I am really happy that you're here. And I'm thrilled and delighted to present our panelists. Starting with Ryan Hess to my left. Ryan is a co-partner of Hess Industries and a producer of in-die clinching products. And to his left is Dave Stoll of Schaeffler Industries. Dave is going to describe how the company uses the in-die clinching in their products and operations. And then streaming in from outer space is Eckhard Fluke. Who of the very otherworldly Eckhard Fluke is going to describe from head of sales at Genoptic, is going to describe the in-die vision systems that his company produces. And one of his distributors, H.A. Rupp of Bruder Industries, is also streaming in. He's going to describe a little bit more about the application of those in-die vision systems. And then to my right is Tom Hutchison of Hutchison Tool Sales. Tom is president, and he's going to describe in-die tapping. And further to his right are Chris Martin, aka Jimmy Buffett, and his son Tucker Martin, who, as we all have already realized, looks a great deal like Benson Boone. He's going to end the hour with a flip of some sort. So they will describe how they are using in-die tapping in their plant and operations. So thank you again. And Tom, would you go ahead and begin and describe your in-die tapping processes?
All right, so we're gonna just have a little PowerPoint. So why in-die tapping? So in-die tapping has been around since the 1970s. So it's a well-proven technology. In-die tapping, of course, you want to eliminate secondary costs. So you're eliminating double handling of parts, floor space that you might need to consolidate parts before you would do a secondary tapping process. You're eliminating that. Secondary equipment you're getting rid of. But really, it's labor cost. You're saving a tremendous amount of labor costs by not having to do a secondary tapping operation. So a few different styles of tapping units. There's mechanical style units and servo style units. Overwhelmingly, most applications are mechanical style units. Our basic styles are our follow along and standard style unit. The follow along is about 75% of the applications, what drives which unit you would use is really driven by how much strip lift you have in the die. So if you have more than 1/8 of an inch of strip lift in the die, you would generally use the follow along style. If you had a flatter running part, you'd use a standard style. But we also have other specialty units, multiple spindle heads if you're doing more than one hole, or if you want to tap horizontally, we could do that as well. So a few different ways that you can attack different tapping applications. So we've got a little 2-minute video here just to kind of give you an idea of how the tapping units function. While you're watching the video, notice at the bottom there's some captions about some design characteristics of when you incorporate a tapping unit into a die, what you'd have to do. So just kind of pay attention to that, and just it'll run for a couple of minutes and you'll get to see, so just pictures worth 1,000 words here. Just to kind of point out something at the bottom, there's tap sensors. You see kind of the brass color there. Tap sensors in the die to sense for broken taps. So that kind of doesn't talk about that, but that's what we're doing there on that screen. There. So, okay. So, and that video is on our website. If you wanted to take a look at that again, it's on our YouTube channel and everything. So the thing though, I really wanted to share with you today is our in-die tapping calculator. Really the two most common questions people ask about in-die tapping is what kind of speeds can I run and how much press stroke do I need for tapping? So this is a very effective tool that we have on our website as well. It's if you just go to our website, it's got in-die tapping resources. There's information on this and CAD files and stuff there. But what we're going to do today is we're just going to discuss an application with these parameters with an M8 tap and strip lift and so on and so forth. So as we go in here,
Am I showing the right thing or no?
Up there, there it is. Yep, that's it. Yep. You actually, you might have to say enable editing at the top there. So, all right. So, yeah. So, Brad, maybe you can help us along while you're doing that there.
Sure.
So, if you go to line 4, can you? Yeah, I don't know if you can eliminate some of that stuff this side or maximize. Yeah,
I don't know why
maximize that. Yeah, maximize that screen there. Yeah.
I don't know how to. I don't want to do that. I'm sorry. Can you see it okay or no?
We can see it, but there you go. All right. So, but yeah, should have on the left side. It seems like something's being cut off. There we go.
I don't know why that's.
There you go. Okay. All right. So see, it's a tap size, maybe in line 5. I can't see that far, but yeah, right there. Yeah, on the drop down list, just put in. Yep. Is it?
So I'm on 6, which is tap size.
Tap size, yeah. There should be if you click on that, it should be like drop down list.
Sorry.
There you go, to the right. Yeah, there's an arrow to the right. There's a, go all the way to the right there. Pick
Okay.
by 1.25.
I'm sorry, which one?
M8 by 1.25. If you keep scrolling, you probably could find it there.
Okay.
There you go. Okay. All right. Very good. And then it says press stroke. Put it in 200 millimeters in the millimeter section. It'll say press stroke. In
Oh,
inches,
I'm sorry.
press stroke in
I'm on
millimeters.
inches. I'm sorry. I can't follow directions.
Sorry. Yeah.
Okay.
And then in the strip lift, it says strip lift in millimeters in that brown section. Put 25 millimeters. Just put 25 there.
Okay.
Then scroll on further down, and it'll say part thickness. I think it's line 17 or something like that.
Yep. Millimeters.
Yeah, so go ahead and put just 10 millimeters in there.
Okay.
All right. And then we're going to scroll all the way down. Keep scrolling further down. All right. And it should have some calculations in there. I can't see that far.
It's a pretty cool tool, though.
Okay, sorry. Again, I just have to stand up. You're afraid. Just can go further up. Go back up to the top again there. So, okay. So in line 8, put in 10. Put in 10 right there, and in line 17, put 400,000 0.400. And then at line 20, put in 1.25.
Okay.
Sorry about this. Is 1.25. All right. And then hit enter and then scroll on down. All right. So, okay. So then you're going to see some calculation. You can see all these gear ratios. I'm just going to try to run through this fast because I'm already taking a lot of time. The gear ratios, there's different gear ratios in the unit. The gear ratios basically dictate two things. One is how much tap travel you get, and the other one is what kind of RPM is generated. And so if you had let's say a press stroke that had 10 inches, you would pick a gear ratio that would be using less than 10 inches of press stroke for tapping, just as a quick synopsis. And then to determine what kind of RPM, there's a red box there that says tap RPM, kind of right in the middle of the screen there, Brad.
Yep.
Go ahead and put like 1400 RPM in there and then hit enter. And once you hit that enter, if you scroll on underneath that, you can see at the different gear ratios, it shows different kind of speeds, how many strokes per minute you can run. So that'll kind of give you an idea of what RPM, what kind of strokes per minute you can run. So it kind of gives you an idea of if I'm running an M8 tap at 1400 RPM, this is what kind of speed that I would be running. So kind of giving a Reader Digest because we had a little hiccup, but if it's on our website and it's something that can be played around with, or you can contact us.
Yeah. Very nice tool. Very cool.
So this is just something that, if someone's interested in your technology, they can play around with this themselves, try some variations. They don't have to call Tom Hutchison.
Oh, no, absolutely good. No, you can absolutely contact us. Right. Yeah, but it is a tool that you can play around. It's like any spreadsheet. You change the parameters,
Sure.
And you can see what you get.
So even while they're in an operation, they can make an adjustment.
It'll help you with if you're quoting a job to give you an idea, but also this is also a practical thing for when applications become real. It'll tell you like feed angle things that we talked about and other information that you would need in production as well.
So the real specifications that you really need to know.
Yeah.
Thank you. That's really great. So Chris and Tucker, please tell me a little bit, tell us all, what prompted you to implement in-die tapping in your plan? What was kind of the beginning stages and
Sure. Well, I think Tom's calculator is awesome. First of all, if you get a chance to use it, it works very well. So, Riverview Products is a mom and pop shop founded in 1990. And we started as a slide former, moved into progressive dies and now fabricated metal products. And I have to shout, I'm anchored by my son Tucker, and I've got Brad back at the shop and my wife Dawn. They do an awesome job. It's really about my team supporting us, you know. So we had a customer in about 2010 that wanted to remove the welding operation. They had a weld nut being spot welded on a stamping. He had worked with a tool shop to build a tool that would insert pierce nuts off of a reel, and it worked fairly well. It had a lot of mechanical issues, but we did that for 4 or 5 years, and then the customer wanted to save some more money, so they came back maybe 2015-ish and looking for another cost save. And we were pretty good with extrusions for self-tapping screws. So we kind of took that technology and combined it with in-die tapping. And then we were able to actually get rid of, not only the first scenario got rid of the weld operation, the second scenario got rid of the weld nut. So fast forward to 2025, we're doing over 10 million parts a year with in-die tapping. And it's been very successful for our operation.
Fantastic. Amazing. Did you encounter any kind of hiccups along the way?
Well, it's a learning curve. So, but we learned a little bit from the pierce nut application to the in-die tapping, and we've used different products, and but we're really happy with the way things are going now. But there is a learning curve, but it's achievable, and we've got good support, from Tom and others to get it through. So.
Fantastic. So are you finding more than one application for it? Do you find your company is implementing it?
Absolutely. Absolutely. So, you kind of start with the one job and then you look for all the applications. And with the struggles of labor today and the costing pressures, it's constant, we're constantly looking at what can we add it to? Where can we add it? So, and yes, we have it in, several applications now that work well.
So what would you say are some of the biggest advantages of doing it in die versus offline?
Well, of course, the biggest one is the labor savings, and then then parts moving around the plant, lot control. There's several things of keeping the process in line and moving forward. So, and the speed. We're tapping very fast.
Speed.
So, I would say an average would be, in the 40, 50 strokes a minute, but many presses have multiple heads. So you're getting a pretty good throughput. So.
Pretty cool. And then what is that done for things like material handling that you probably had to deal with previously?
Well, again, it's a lot of lot control savings, so just managing where the parts are in the pipeline, and we're having a lot better success with we had offline tapping with what tap machine did it come off of, and what was the wear on that machine, versus now it's all contained and the product comes through the tap, so basically production control, lot control, and moving the parts around, logistics.
It's helped us so that lot control is even more important to you than the time savings. Would you say that's true?
Well, I can't, because time saving is money. So but definitely the customers and in our plant control, definitely the lot control is extremely important.
And who are some of your customers? I don't mean by name necessarily, but
so we're in the we're in automotive, we're in office furniture, appliance, and we have some military. So we kind of spread it out. Not all those are using in-die tapping, but I would say the 3 or 4 major ones are we use it all over. So,
do you find that using in-die processes in general, that it's sort of a value add that you're able to offer more than just kind of piece parts, but assemblies that?
Well, absolutely. So we're pretty vertical with our tool design and building, and Tom's helped us, get to where we are. But we look, every time we build a tool, we're looking at, all the techniques. It's in-die sensoring, in-die tapping. We're not doing insertion right now, but we'd love to do it if somebody wants to send us some parts. To stay competitive, we need to use all the skills available.
Interesting. Are there some of the specifications that kind of surprised you? Tucker, I'm going to throw that over to you. Since you're the engineer at the group here. I don't mean our group, I mean your company. Are there, some aspects of the process that surprised you or that you found that maybe you fed some of the specifications into this calculator and found some surprising results?
Yeah, the calculator is an excellent resource that's really allowed us to kind of understand the process better. And they've been excellent helping us to answer any of our questions. Just the resources are great with it.
Have you found any differences in materials over the years?
That's what are some of the, well, you got different, all your different materials, different thicknesses. So even just down to the threads. So there's really a lot that goes into it. They've got it very well covered.
All right. What kinds of materials are you using now?
Oh,
I'm sorry. Yeah, the tougher ones.
Well, everything has its unique challenges. So, we're using 1008, 1010 cold roll, and you have a pretty common size, and you're in good shape. Each thing has its own flavor. So I mean, people in the industry know that everything has a learning curve, or you're going to learn it. So nothing's that hard; it just has to be done. So.
Great, cool. Thank you very much for that. Brad, do you have some questions from our audience?
Yeah, thanks, Kate. I do have a question, and maybe the Martins or Tom can address this. I'm wondering if, I'm imagining that not every offline tapping operation can be moved in die, maybe based on part design features or access to a particular. Well, Tom or the Martins, do you guys see maybe part redesign if somebody wants to move an offline tapping operation to in die?
I would say it's often hard to redo an existing die, but it can be done. People put on a bigger die shoe, they'll kind of separate, put on a bigger die shoe, but overwhelmingly, most people will probably design a die from the get-go with the intent of in-die tapping versus trying to retrofit an existing die. It can be done, but it's not as common. It's probably more what drives in-die tapping more so is just the volumes. You have to have enough volume to do in-die tapping. So if you're doing a part that's only 10,000 parts a year, you're probably not going to do in-die tapping. But if you can justify generally the cost of progressive die, you usually can justify the cost of in-die tapping. I'm not saying always, but that's kind of a good thumbprint or thumb rule of thumb that if you can justify an product die, you can justify it.
So, Chris, are all your in-die applications originally designed into the die, or have you ever tried to retrofit it?
Well, no, the case study I gave was a transition, but we did develop new tooling at each step.
Okay.
The only thing I'd add to Tom is that the cost of labor today, that volume cross section of when it makes sense has gotten lower.
It's gotten lower.
So we constantly look at, we would rather make a capital investment of the in-die tap than add labor to our processes.
So other than volume, what are some of the other parameters you look at before you decide to invest in a in-die?
Oh, I don't want to cut Tom. Tom's the so the package, the envelope, the tool envelope.
Yes.
So how much real estate can you use and stroke and speed?
Yeah.
Go ahead.
No, but you're right. I would say if you're doing, let's say, 1 or 2 holes, you absolutely now look at in-die tap. If you had a part that had 15 tapped holes, maybe it wouldn't be realistic because you might not have enough die space to fit enough tapping heads in the die to do that. Certain materials as well. So, like Chris is talking about speeds. If you're tapping stainless steel, you can only tap stainless steel, let's say, at a third the speed of mild steel. So, if somebody came to us and said, "Hey, I want to tap 3A16 thread at 75 strokes a minute stainless steel," it's not realistic. You can't run stainless steel at that speed. So maybe you couldn't do it in the die because maybe the press time might be more valuable than the savings of eliminating secondary operation. But then it's less common that overwhelming most applications do justify in die tapping, but there are some that do not.
Okay. And Chris or Tucker, can you recall a project where maybe you priced it out with offline tapping and in die, and maybe talk about what the ROI looked like when you decided to go in die? You know what I mean?
I can't think of any
The project?
specific ones, but I
No.
just like the general statement is that it continues to get lower. The ROI comes faster because of the
Okay.
labor and the other things I said, lot control and logistics. It just makes a lot more sense today at a lower volume than it did when I started in 2015.
Sure.
What would you say, like average cost of a secondary tapping operation? I'm guessing 10 cents a part or thereabout. But just
Yeah.
So if it's 10 cents a part and you're doing 100,000 parts a year, it's $10,000. You're not getting that far away from really justifying it.
Sure.
And so I just suppose every application is a little bit different, but probably 10 cents a part is a pretty realistic number about what a secondary tapping operation.
So we started this earlier at 8 cents, moved it to 10, and I'm still going to challenge Tom.
Yeah,
that
it might be more.
If I took this through our ERP system, it might be more like 12 cents now, or, yeah. So it's definitely moving up.
Do you find quality differences?
Oh, the in-die tap is way superior, to the secondary operations. But being contained in the product die gives you very accurate, placement to tap, so.
Yeah, we talked about that's a common question people always ask about in-die tapping. It's like, oh, you're breaking taps, because they think, oh, it seems like a volatile thing, but we were just talking about how they never break taps because, a prog die, your alignment is critical. If you don't have good alignment, you're not making a good part. And any tapping operation is all about alignment. So the alignment is perfect. So if the tap is lining up, you're not breaking taps. And so it seems counterintuitive, I think, to people when they talk about in-die tapping, about not breaking taps, but in reality, that's pretty common that you don't see a lot of tap breakage.
Well, I called back to Brad for the technical backup, and he says we've never broken a tap. And now you're talking about,
I can't guarantee that will not,
but for our applications, and we're talking about 100 million parts.
Yeah.
So
not out of one tap.
no,
Like what kind of tap like to you?
So I checked with Brad, and he said our average is about 20,000 cycles per tap.
So then when you're approaching a customer, is that part of your value proposition to them that, we have this additional quality because of the in-die tapping?
Oh, absolutely. Absolutely.
Space.
Again, we just do not want to add labor. So for us, it's almost partly being cultural. We will try to drive the customer to the end result that we want, because basically labor and quality, so.
Because a big thing, quality is a big thing, but just not missing a whole tapped hole. So it's and the die you can usually monitor to make sure the hole's been tapped. Whereas sometimes the secondary operation, you go and the guy just forgets to tap a part, and all of a sudden they get shipped. When you're monitoring through the process, you can make sure that the part gets tapped.
Absolutely.
And the last thing you want is a shipment coming back and say, "No, we found one that's not tapped." Now you have to sort them.
That's not good.
They're going to see if there are any others. Who gets that fun job?
Oh boy, draw straws.
Straws. Well, that's really fascinating. Thank you very much. That's really great. I think we're going to go ahead and turn now to Ryan. Ryan has some Hess Industries. Ryan, tell us about your in-die clinching process.
Yeah. So, like I said, I'm Ryan Hess. I'm co-owner of Hess Industries. I'm here today to talk about our brand clinch solutions. Where we install in-die fasteners inside of a stamping die. So that is either progressive die, transfer die, or even single hit dies. So I'm going to just kind of breeze through this presentation here just to kind of give some information. So what is in-die fastening? In-die fastening is the process of automatically installing fasteners within the stamping die during the press stroke. So every time that press goes up and down, we're able to install one or multiple nuts in that press stroke. It eliminates the secondary operations, and it's able to do it with precision, speed, and repeatability. So why in-die fastening matters to manufacturers? It saves time, reduces labor, improves accuracy. Like Tom was saying, in frog dies, you're already guiding the strip using pilots and holding it in a precise location. So we're able to then install the fasteners in that using guiding the nut through the whole nut or stud in guiding it through the whole operation to where it's able to hold that repeatability. And then, of course, there are cost savings by not having that secondary operation of that additional labor, additional floor space. So then traditional fastening methods and their limits. Traditionally, you have a secondary operation that you have is very labor intensive, and it can be slow depending on how that laborer is feeling that day, or there's a lot of elements that can go to that. And you also have the chance of having a human error there with the manual insertion. There's also a common thing would be weld nuts, but you can have heat distortion. You're heating that weld into that part, especially on thinner materials where you can see that heat go through the part. Also, it's traditionally slower than a clinch nut because you have to give that weld a time to bond to it. And with having that heat, you can have inconsistent welds causing quality issues. So our solution is in-die fastening. It's built to fit your press. So we can fully integrate it to your existing press. We can do clinch nuts, clinch studs automatically. And the heads are custom designed to whatever stamping die that you would like to put them in. And to touch on again, in these dies, we're already guiding the strips or holding the part in location to stamp it. We're able to repeat to be precise and repeatable fastening the So let's take a look at how the process is. So the clinch heads are installed into the stripper of the die. So they actually move in the top shoe of the die, and they are moving on the stripper plate. Those heads then are connected to our clinch solution speed system using the quick change couplers that you see on the screen there. So what that does is it makes changeovers very easily. So you'll see in that automation, we're disconnecting the bottom hose. That is the hose that the nut, stud, fastener are traveling through. And then right above that, you'll see the other clamp. That is where all of your pneumatics, your sensor, electrical is ran through. So in a changeover situation, per head, there's 2 quick clamps that you're able to do and able to quickly disconnect those heads from your die to do a quick changeover. So then we're going to switch over here to the feed system. The press operator puts the fasteners into a bulk hopper in the system, and then from there, the system does the rest. The fasteners then go on a ride through a conveyor system into a slide feeder system. The slide feeder is actually what orients the fastener into the correct orientation, so that way the dovetail and the magic of the nut that creates the holding of the clinching process is oriented in the correct orientation. From there, when they're in the correct orientation, they then go to a distribution hub. And then as there's sensors in every head of the clinch operation, and as it calls for more fasteners as you're going through your stamping process, it is then air solenoid fires compressed air into the shot tube, which then drives the fasteners into the clinch head. So it comes through a distribution system. There is then an escapement system that feeds it into our shot tube. And then, as it says there, compressed air is how we get the fasteners from the feed system to our heads. So then as the press cycles, the in-die clinch heads install the fastener into the stamping, creating a strong, permanent mechanical bond. So here kind of shows what the operator sees as it's running. So you can see on the screen there, we have all the different sensors in the system. So they're able to actually monitor what the system is seeing. If it does have a fault, it comes up on the screen to kind of walk your operator through what they need to do to fix it. And just kind of shows it everything that is running smoothly in that feed system. So fastener selection is critical when it comes to in-die fastening. The system is built around the fastener that you choose, that you would provide for us as we start to design your system. That is very crucial because it is how we optimize how fast we can feed nuts into the system. Tolerances is everything in this. As you're trying to move the mass of those nuts, studs, whatever fastener choice you have, the more tolerance you have, the more room you have for error. So we design the system to the exact fastener you provide, so that way we are able to maximize efficiency for your system. So here we kind of show the clinch nut versus clinch stud. We have systems that install both of those. The clinch nut, here's kind of a show that as the ribs are compressing into the stamping, the material starts flowing into a undercut on the nut, and that is how it creates the bond that installs the nuts. They have to be pressed into a punched out existing hole. So in the previous operation, we have to have a hole for that nut to go to. They are these applications, they are not self-piercing. During installation, the force of the press, so it uses the press to create that bonding force. The metal is then able to flow into those undercuts that you see the arrows pointing to there. And again, that is what creates the mechanical bond that allows the nuts to have that hold until a fastener is installed into that nut. Creates a strong mechanical bond. No welding or tapping is required to hold that fastener in that part. Clinch studs here uses pretty much the same technology when it comes to the clinching of there's that star pattern in there that they use as an anti-rotation, but that also disforms the material to form it back into that undercut that holds the fastener into the existing hole. So clinch studs are externally threaded fasteners pressed into a pre-punched hole in sheet metal. And then, yeah. So here is a animation of our stud heads. You can see there in that blue tubing in the top left corner, the stud coming in. It's then fed to a set of fingers that feed the nut forward for the press to stamp that in. Unlike the clinch nuts, the stud feed system, it feeds the fastener sideways through the shot tube and then rotates it in the head. There's a set of fingers that are controlled pneumatically there. The fingers then advance the stud forward, so that way the press is able to push the stud into the part using typically a nitrogen cylinder above that. It's a slightly slower process than clinch nuts, just because with clinch nuts being a round, they're round in the correct way for what we're trying to do. We're able to fire them faster. Where the studs are longer, they're a little bit more cumbersome to kind of move around. So traditionally the studs are a little bit slower than the installation. So our tooling is built by tool makers. We have journeyman tool makers throughout our whole shop. It's built for tool makers for tool makers. So we understand the designing and everything that comes to working in a stamping facility, that we build our products with that in mind. So as Hess Industries, we have our branding Clinch Solutions, but we also partner with Hutchison Tools, and we do build their in-die tapping also. So we have a lot of technology under one building that we're able to put into our products to give the best to our customers.
It's really great. So it sounds like a lot of development went into this process.
Yes.
How long were you not?
So we've gotten into in-die clinch in 2018, and we've had customers ever since then, and we just keep developing it more and more every day, just until it can be the best for the customer.
It's really great. It's really great. Thank you. So Dave, not Dave Schaeffler, Dave Stoll. Tell us a little bit, first of all, about Schaeffler Industries. What kind of volumes do you produce? Who are your customers, and so forth?
So Schaeffler is a worldwide manufacturer. Schaeffler here in the United States is based in Worcester. Our headquarters in the United States is in Worcester. In Worcester, we manufacture torque converters for the big three automotive here locally and in Michigan. So torque converters, every internal combustion engine vehicle has a torque converter, and we ship thousands a day from our plant in Worcester.
How many?
Up to 5,000, 6,000 torque converters, complete units. It's just a hydraulic disconnect from the engine to the transmission. So there's many stampings go into one of these torque converters. So we're looking at value added for the assembly lines, not just a stamping facility that supports the assembly lines. We have in-house tool design, in-house tool manufacturing, in-house tool development, and in-house tool servicing. For the big picture is the torque converter's got to be productive and profitable going out the back door. So we're looking for value-added solutions for the customers in every project that we do. So big numbers, what we do. Not every part has clinch nuts or studs, but we do a lot of them, and we've done a lot of them for a number of years.
Great. So please tell us a little bit about what prompted Schaeffler to begin to use die casting it.
So that's part of our value added. The customer came to us with the interface. This is the interface we need for our torque converter to their vehicle application, and we need to insert these nuts or studs for that. Originally, we had secondary operations in the lines. Those were always a bottleneck. They're always slowed down. There's a lot of variables. You have the operator variables. You have nut variables. You have all these different variables that we have to deal with later on. And as the other team members here have said, anything you put in the die becomes much less variable. The dies are set up and designed and built for location, for accuracy. So every time we can put one of these into our dies, it's much more accurate. We're looking for quality issues, for accuracy, and we don't want to slow down any one of the processes. So if we add it to a press, add it to a transfer press or a progressive press, we don't want to slow those presses down either. Originally, they were a bottleneck. If you added these to a pressing operation, the press slowed down, which then press room became much more interested in how do we speed these up. This where our partnership with Hess and Clinch Solutions, and I want to stress partnership because we work together very well, and they're in our shop, we're in their shop. Talking about the challenges, talking about these
problems we have talking about speeding up, what's slowing us down, and again, the partnership that we have with them has greatly increased our stroke per minute.
By how much, Eddie?
I would, generally speaking, 10 to 15%. Just raise the press speed up from our older solutions.
So you tried some other solutions before?
Yeah, we actually have some in-house designs for some of our studs. So our own design, and we also have other customer solutions for that we originally started with in the clinch nuts. Again, I want to stress the partnership. Anytime their proximity to our shop has got to be a benefit to us. I don't think that's a hindrance for them going nationwide or even worldwide, to be honest, because of their interest in making sure everybody has what they need.
So this industry didn't just drop it off and say, hey, it's lights out.
No, absolutely not. There was a lot of development. Like he said, I believe that you probably got in the market in 2018, but we were talking about it before 2018.
Yes, we were.
Many years till we actually got one of their products and one of our combined solutions into the tool.
Yeah. What kinds of problems were you having with the previous systems?
Problems probably originate in the bowl feeders getting the nuts aligned. So we see Ryan talked about the bowl feeders, getting the nuts all in line, getting them through the tube in the right direction. That's probably the biggest hiccup that we have seen over the years. But also getting enough cinching force to ensure the nuts don't fall out. We have zero fallout. We cannot afford to have any nuts fall out. Zero. So because this is a customer interface, we would have a customer complaint, every customer complaint has a value to it, cost to it.
What problem could there possibly be?
Well, I always say if this car breaks down on the side of the street, my wife is calling me first, and I don't want that call. I don't want my wife to get stranded on the side of the road. If I make quality products, at least it's not my product that's stopping them.
Excellent. Good. Very good. Success story.
Yeah.
Brilliant. And
Yeah, one big success I want to kind of touch on that we talked about earlier is in their online operation, they installed one nut at a time, and they had their die that they run one of our products on is 6 heads at once. So every time that press makes a hit, it's installing 6 fasteners. So what they used to have to do, orient that part 6 times by hitting it 6 different times, they're now able to do in one hit. So that has sped up the process.
I would say.
Very much so. A lot of value added once we did multiple hits.
Very good. And so, and you're in a unique position that you got customers, big trade. Doesn't get much bigger than that. Did that, and we all know that in the automotive industry, there's huge competition. Huge competition. The automakers are always pressing you to look for efficiencies that will save them costs. What would you say that that kind of helped Shapler become as big as it is, in the sense that you're able to maintain as customers? Is that value add? Is that part of your sales story?
Yeah, value added. I think quality is a really, really big one for the automotive industry. Schaeffler does not take quality as second. So because of Schaeffler's stance on quality and the need for quality and value added also. But I would say that that's probably the number one value added is the quality for adding these in die.
Interesting. Yes. So, Brad, do we have any questions for Ryan or Dave?
Yeah, we sure do. First off, just as a general question that I'll answer, so the question is, will the attendees receive a PDF of the presentation? We won't send a PDF of the entire event, the individual PowerPoints, as long as Ryan and Tom are okay with us including them in the follow-up email that we send to the attendees. We can include those. And then a recording of this event will be on our website. We'll have that up on the website within the next couple of days, so you'll get an email from us with a link, should you want to go back and watch this again or show it to others at your company. So I hope that answers your question, Jason. Questions for the panel then. Ryan, are customers limited to only clinch style fasteners, or can other types of fasteners be applied here?
I'd say clinch is the majority of what we do, but we're always open to looking at different applications if we are able to help the customer to their need in that application. I would say the majority of it rides around that clinch.
Okay. And then with a single hit tool, what's the recommended minimum spacing between holes?
Say that again.
With a single hit tool, what's the minimum spacing between holes? How close? Yeah.
I would say that that's specific on the size of the hole. Probably 2 times the hole diameter. Be just a rough guess. Yeah. But it would be specific on the size of the hole. So if you're looking at an M12 or an M4, you would have a varying. But yeah, I think probably 2 times the diameter of the hole.
We're able to build the tooling kind of, again, that kind of goes with what I was saying. If we built the tool around the nut, we're able to do some tight spacing. There's definitely some limitations there, but when you come to us or quote, we ask for a strip layout. What's the part look like? What fastener are you trying to use? There's a lot of things that go into that. I don't know if there's a immediate answer to that for every application, because every application is different. But there's we can get fairly tight.
Yeah, I would like to. If I was presented with a part that had clinch features that were closer than that, I'd be worried. I would be worried, and I would be talking to Ryan about what other solutions can we do, or what else can we offer and feedback to the product design team.
Yeah. So there is different things we can do in that. You can install fasteners in different operations. So rather than having the heads kind of beside each other, you can have one here, and they're installing the fasteners close. So to say there's the limit there would be material distortion. Is that material going to flow because you have holes so close together? Well, when you clinch this one, is this material going to be pulled from that one? So again, to give a clear answer, I would have a hard time, but there's definitely solutions we can't do.
Might depend on the material type too, right?
Look at different option. Material type does have a big play in that, just because different material flows different when you are forming it in a press.
Okay. One more question has to do with error proofing. So when there's misfeed for the fasteners, is there some sensing for that in the insertion head itself, or does the user have to use external part presence sensors in later die stations to identify a misfeed?
Yeah, so we always prefer to put a proc sensor later on in the die to make sure that you have that nut is installed in your part. That no operation perfect, but with the system we have built, we have very good success with that. But there is, in any automation tool, there can be mistakes. Most of the time, human errors. Did they start the system before they started the press? There is some like that. So we do suggest that they put some sort of sensing system next operation, few operations down. That way, if they do have an error that did not get installed, it shuts the press off instead of making a lot of bad parts.
Is that what you guys have, Dave? Yeah.
We also have, it's like he said, if something shuts off ahead of the other, so if the whole feeder shuts off ahead of the press, or if something, because we all know that production sometimes shuts off when it shouldn't. Sometimes you have a double nut or double stud situation. You got to make sure you're not putting two nuts one on top of the other, because that becomes catastrophic in a tool. two studs that don't fit in a hole super well. So electronic sensors or evacuation processes for that, we definitely put in a tool.
Okay.
I would say most of those, as he's talking about double nuts and those issues, as we see those, most of the incidents that we see in those applications are human error. If somebody didn't clear the die, they thought it was clear. So that's where the sensors can be a catch-22 of you don't want too many, but it's also can be a saving grace in these as we're shooting fasteners into the die. It's nice to have something there to say, don't make another hit. There's one there already. That can save you from a catastrophic failure of trying to put two studs in a hole.
Sure. Okay.
So, one of these we talked about earlier is, so how does this process compare to, a weld nut insertion? What would be the advantages of the clinch process versus weld nut?
Yeah, so I touched on this a little bit in our presentation. The weld nuts traditionally is an offline operation, so it kind of adds, again, floor space, more labor. It also can distort the part from heat. And versus the clinching, we can do end die. We're able to kind of eliminate that need for a secondary operation. And you don't have the heat getting put into the part that some parts can be a little particular about.
I can elaborate a little bit on if we're talking about end die welding versus end die cinching. End die welding becomes a little bit cumbersome, isolating the welder from the rest of the die. So you have electric currents that you don't want to mix with coolants that a lot of dies have.
Yeah.
You also have dirt. Weld comes with splatter, and dirt. We all know dirt and tools is not a good thing.
Yeah.
So the clinch system is very, very clean. We see no dirt, particles, slivers, those kind of things come from the clinch nuts, which we've been part of some end-die welding, and those are some of the challenges. You also have disposables that come with welding. You have disposable weldings, coppers, the other things that are, yes, value added, but yes, expensive. So in my opinion, the expense of the gun is cheaper than end-die welder, as well as the isolation and those kind of things.
Well, you mentioned the distortion too. I just looked at, some of the pledged products, and I was really surprised that I did not see much distortion. How do you avoid that distortion or prevent it?
So with the end-die clutching, your starting hole is very crucial. The nut supplier typically will give you that information. We do not supply that information because the nut supplier has done all the testing of what size hole you need to get the correct clinching pressures and holding force that you need. So having that correct hole size is crucial to not having that distortion, because they calculate how much material you need in there to create that correct material flow.
So along with that, your shear, your breakout, all very, very important on which side of the part versus your cut is the nuts going in, because the shear side is always going to be more accurate than the breakout side. Those are all things that we've developed along the way. My team has developed along the way for our processes, and anybody that would implement these into a tool would develop their own process, their own guidelines for those holes. But as Ryan said, those holes, the starting point's given to us from the supplier of the nut. That also dictates how much torque out, how much holding force, so that these nuts don't fall out. You also have to worry about burr and rollover, those kind of things. So those are things that we're monitoring and watching along the process to get that process to go perfectly. Again, once they're developed, they're very, very accurate, very, very repeatable. So,
Fantastic. Thank you very much. It's fascinating. I'll be saying talks more, but we need to move on. Speaking of monitoring.
And I do have two more questions for these guys, but we'll save them for the end so that you can just kind of let the people know that are asking the questions. We'll ask them at the end.
And now we'd like to speak with Eckert Fluke. Eckert with Genoptic Solutions. Eckert is joining us from Germany. Thank you, Eckert. It's probably way past dinner time for you right now.
Depends on dinner time, yes.
Dinner time. If we hear some stomach growling, we know where it's coming from. Anyway, thank you, Eckert. Please tell us about your in-die inspection systems, how they work, and so forth.
Thank you. Yeah, it fits perfect into what we heard up to now, because we saw already that more and more functions are in the die, that it's more condensed with more and more technology. And this means on the other side that it's very important to monitor, to check the parts, to check if any manipulation in the die was acting correct, especially when the speed comes up and you make more and more parts. So we're doing this since over 30 years. Well known under the name Otto Vision, also in the United States, I think here and there. And since 2018, we belong to the Jenoptik Group. And we're focusing on that point that we have the idea, especially in the stamping, that we want to set the people free of the bondage to wait for data, to come back. So somebody always going with their parts back and forth to some kind of a comparator, then goes back, makes some adjustment and whatever. And our systems are controlling 100% every part and give out a lot of results. And so even in the setup period, when you work on the die, when you start with your machine, you can see the data. And finally, you give the start for the production by just make a last check, maybe in the test room. But all the time you're using these automatic systems. And we will come back to in-die and cameras in-die. This is what we want to finish up with. But I wanted to show just this progressive die production for USB connector, for example, and wanted to show that at the end on the right side, this is a last decision. If this part will be part on a reel, will be winded up on a reel, then this will be a station which will not cut it out, or it will be cut out and then it falls free, what we call like a free-falling part. And we have chances to check parts after the die, and it is always the first thing that everybody tries to. When you have parts on a strip, you try to make a control, you try to check the parts automatically with something like a test station. But when we dig a little bit deeper into how fast test stations have come already, then we find out that there's a absolutely need for something to do also for the in-die. Because here you have the chance to check parts by leading them in front of cameras and to find out bad parts, to indicate them, and to cut them out individually. This goes so far that when we will see it now here, we follow a bad part, maybe because some problems in the material or whatever, or scrap came up, whatever, these parts will be cutted out. And then you need to make a decision. You either connect again your strip, or you allow to put some bad parts on the reel, however. But it is some kind of an interrupt. So this was leading into a totally new development of a system that is cutting out bad parts by laser, and with the same laser weld the strip together again. Always with the idea to have the press run all the time, to give you the opportunity to work on it, to extend the speed, to work on the feeding, to say, okay, we will improve the quality without stopping the press anymore. So, and this means for parts on a strip, we have a solution that can find bad parts, can analyze every part, check every part, can sort out bad parts, can sort out even a section, cut out a section of strip, and you have the press run all the time. And this is how we come to now, what about the in-die? And the funny thing is, this machine you see right now is just a few years old, but the in-die technology is coming out of the 90s even. So I was involved in that. in the 90, 94, 95, 96, during that time, when we had the problem that we at high speed were producing loose pieces, parts that are coming out of the die and were flying on a conveyor belt and then into boxes. And when you had any problems with material or any problems in the die, you could never catch them again. So, and this is what I want to show. This means instead of having functions in the die, which you have anyhow, you have some kind of a bringing in other material, combined material, putting in, as we have seen now, things right now. We insert a camera. What you see on the left side is the module, production module, or modules, could be some more, depending on the parts you produce. Then the camera in-die module, the blue one. In this case, it is looking down or top down, like in a comparator. And it's really for measuring. It's not only contour check, it's measuring different dimensions. And then you have a control sorting unit here on a Bruder machine at an exhibition. So very nice tool to show it. It runs at 1,000 strokes. And let me say what I said often, speed is relative. So 50 strokes can be very fast depending on what you're doing. 2,000 strokes can be very fast depending on what you're doing. It has to do with the parts, with the strip, with the feet lengths, whatever, with the process. And in this case, we have now a contact part running at 1,000 strokes. And this die was made in a way that we can show it on exhibitions also. We have a manipulation button. I will push the button right now, and it produces 5 bad parts. This means in the die, we're shifting something out, and now the punch is not working as it should, and you will see an opening now in the contact. So we show this in slow motion. Here it comes, 5 bad parts in a row, and these parts will be fished out. So what does it mean? When you have any problem in the die, when you have problems, and most of the time it comes by raw material in between, because raw material is getting more and more bad worldwide. I'm interested in feedback also from the other partners and guests. Raw material is a critical subject. So you can have a lot of good parts and suddenly you have a change. And if you are able to fish these parts out, here, now we see the bad part section is on the left side. If you fish these parts out, you catch them, then you have a box of only good parts. And a box of good parts, guaranteed good parts, has a different value, has a different price than a box which tells you 99.733% or something like that. So that's the idea, to get rid of that sorting, of that going back and forth to check with some quality checks only with XR charts, XS charts, which you can still do to study your process, but to make this as a guideline or as a judge for do I have good parts or bad parts in the box, we would say this is the right method to do that. So we can show here a little bit what is inside of such an in-die module, the camera inside, lens, illumination, and whatever. But I don't want to go too much into the application because AJ will pick that up. I'll finish with the last slide of mine. You see on the bottom what you have seen in the video. There's another model here with 2 cameras inside and some key facts. And I would give the ball to AJ Rupp from Bruder.
Eckert, that is fascinating. And I did want to remark that Eckert led the team that developed this technology. I think
in the 90s, yeah.
Most of our audience is probably familiar with, inspection systems offline or immediately following, not actually in the die. This process, Eckert and his team had developed this process 20 years ago, but I know that everyone's really familiar with that. So to give you a lot of credit for that, Eckert. So AJ, please do proceed and tell us a little more about the applications of this process. AJ?
Sorry about that. Can you hear me?
Hi.
Yeah.
Thanks for joining us.
So yeah, thank you for having me here today. And again, I'm Lois Rupp. I'm the president of Bruder Machinery. We've been partners with Genoptic Auto Vision Division for over 20 years, and we're responsible for distribution and service of their products within the Americas. I've prepared a couple of illustrations where we've used in-die vision systems for our customers, starting with the one you could see in my presentation. The first one here is an automotive application. Parts being produced are self-lubricating bearings that are used in transmissions, steering columns, and other areas within the automobile. This particular die configuration you see here, it's a module die. There's 4 modules. First module is the stamping and forming module. And then we get to the in-die vision system. The first of the 2 in-die modules is for dimensional inspection of the components. And the second is for surface inspection, as these parts have a coating on them for the lubrication factor. And then the final module is basically part clip out and down stack. This application ran at about 400 SPM. And as Eckhard showed previously, we were separating the bad parts from good parts, so the customer had only good parts. The major problem this customer had was they had very little control over the coating process. So the big benefit they got from the in-die vision system was they had only parts that had absolutely proper coating were going into the good bin, which made a big difference for them. Because if part got through that wasn't right, it was, big trouble down the line. A little close up on the vision systems, a little different than Eckhard showed. In this case, the cameras were on the top, looking from the top down, also with a mirror arrangement. And we, on the right-hand side, you could see how we set up the HMIs. So you had the press control and the vision HMI right next to each other for ease of use for operation. The second application I'm going to share with you is a consumer product application. This is for a razor blade. This is far more complex, where you have a progressive die with 6 modules. You're doing your stamping and forming. There's an in-die cleaning module here. Then you have a component supply coming from outside that's getting married to the stamped and formed strip. And then you have a laser welding system where you're welding the components together in 16 points. And then you have a break-off station, and then you have your final inspection system. This tool was running at 500 strokes a minute, and the in-die inspection system was not only checking the parts for dimensional accuracy, but also verifying the 16 welding points were where they're supposed to be. These are some pictures of the actual die as it was built. You could see the inspection module on the end there. It's the last thing that was done before the parts came out and went to the assembly machine. Again, this guaranteed that we had 100% good parts flowing downstream. This is just an example of a system we recently did with Genoptic, where we're using vision systems on the front end, the back end, and in the die. We are checking on the front end, etched. It's an etch strip coming in, so we're making sure the strip is in proper orientation before it gets into the press. In the press, we're stamping a channel. This is a medical product that actually enters the body. And we are taking a look at that channel within the press. Then we're coming out, cleaning it, and then again, a final inspection post-cleaning to make sure the parts are perfect before they're final packaged and shipped out for assembly. And lastly, Eckhard's going to be with me in Chicago this year. We're going to have our PSS 40 LC-LW and in-die technology on display during the show. Any questions?
Yes. Well, speed is an issue, right? Of course, many of us are familiar with your high-speed presses. And you mentioned that that particular system went as high as 400 SPM.
Oh,
What are the parameters, or what are the limits, and how does speed factor in?
we're not limited by speed. You know, normally the dies are the limiting factor. There's other factors in production that limit the speed, not the vision system. We have inspection systems out there running over 2,000 parts per minute. Obviously, it depends on the level of inspection and detail that we're looking at. But for the most part, the vision system's not a bottleneck when it comes to speed.
Amazing. And I imagine that those speeds, having a vision system in die as opposed to post die, is probably very significant.
It is, especially in certain applications, because you can prevent a lot of downstream problems by, doing an in-die inspection. You have a bad part before before you get to packaging or the parts go any further down the line. It's depending on the application, especially automotive and medical, it's a huge savings to the customers.
Great. And then you mentioned a coated application.
Yes.
Do coatings present any kind of a problem in terms of inspection, in terms of that reflection or anything like that?
I mean, the coatings make it a little easier. When they're not coated, sometimes reflection can become a problem, especially for surface inspection, looking for like very minor scratches and stuff like that. That's always problematic because it depends on the lighting, the camera resolution, and there's a lot of factors that come into play there. But in the application I showed you, it was a coating, and the coating was colored. It was a red coating. It's a proprietary coating to the customer, so I don't really know exactly what it was. But and as I mentioned to you, they were getting areas on the strip where they were missing coating, or there was too much coating, and that we were able to detect very well with the cameras and eliminate those bad parts from getting into those final, components, whether they were transmissions or steering columns and whatnot, because you need to have 100% control over those components also.
Fantastic. Brad, do we have any questions for Eckhard or Elaps?
So, okay, we do have one. So, does the same laser that cuts out a bad part from the strip also weld the strip back together so you get continuous production, or are there different weld components?
Okay, that system, that's a special thing, and we are patented on that. It's the same laser that is doing the cutting and the welding. Nowadays, lasers can be controlled very specific. They are at the high speed if they pulse, and you can control them in pulse and then in continuous mode and mix it and everything. So it's the same laser.
Very good. We do have two other questions back to clinching, and then if anybody has questions for these guys on the in-die inspection and the camera systems, we've got a few minutes left for some more questions. So, maybe for Ryan, when a stamped part contains multiple clinch nuts, say 3 or 4 of the same size nut in a system, can the system feed to multiple locations on a stamped part, or does it require multiple clinching systems?
So each one of our systems are a 4-out, up to a 4-out application. We have seen where there's need for more than 4 in a stamping on a single hit. We're able to then do multiple systems, but for a single system, we're able to feed up to 4 fasteners out of one slide feeder system.
Okay, thank you. Back to Eckhard and AJ. Can the inline inspection be integrated with transfer presses? Do you have transfer applications?
You're switched off if you talk.
Sorry, we have not put a vision system on a transfer press here in the States yet, but there's no reason why we couldn't.
Yeah. we have done things that goes into that direction because we have some experiences also with other environments. Because also many times on the transfer press, you work with a lot of oil and things like that, and we have their different experiences. So if a customer has an application and wants to enter into it, we're happy to talk with them.
There you go. Okay. In-die inspection. How does the lubricant affect the effectiveness of the in-die vision system?
Okay, there are some tricks that we have to make, or we had to do. Let me say in general, lubrication should be controlled, should be the right kind of a lubrication, not to use oil as much as oil could be, but as much as needed. And then there's typically that before the position, when you check some dimensions that have to do with contours, there's typically something like a blade, like an air blade with pressed air, blowing free, and then in that moment it's okay.
Good, thank you.
But it runs.
Yeah. Okay. All the way back to Tom Hutchison, maybe when it comes to taps, maybe the Martins have some input on this too. How do you know when the system when you're at the end of the life of the tap? Can you tell from the whole characteristics, or how do you know when tap life is becoming an issue, Tom?
Yes, so you're going to gauge this right with a go no go gauge like you would do for any tapping. Periodically you'll check the gauge. I know we talked with you guys. I think most companies will start to figure out a certain number and then they'll change the taps automatically. So Chris mentioned they're getting 20,000 holes out of a tap. So many customers would say, okay, maybe then at 18,000 holes, we're going to change a tap so that we just know that we're not going to have any bad threads going through. But generally, people will check with the go no go gauge periodically, whatever that is, every couple of minutes, or whatever their system that they've set up. That's how we check.
When I think there's been some common themes, and I misspoke a little bit, and Eckert brought it up. The speed is relative. So when I was asking a question about speed, that was for one specific size in press stroke, right? And so the materials and the size of the tap and the stroke are all going to affect that speed, and I was focused on one thing. So speed is relative, and then I also think that having good holes, control of your hole, control of if you're extruding, control of your extruding, and again, accurate or lubrication, all that needs to be controlled to make these processes successful.
Yep.
Yeah, hole size is super critical.
Super critical, right?
And alignment.
Alignment, lubrication.
The maintenance plan,
Right. And we do have one more so far, anyways, for Ryan. During the clinching process, is there a way to measure and track the force being used to insert the fasteners as maybe a quality check? Can you measure the force in process, or that's not a thing?
I'll take that one. Yeah, there's most parts have a certain amount of requirement for a torque out or torque through. It's two different things. So if you're pulling the torque through the part and actually pulling the cinch into the part, that force is much, much greater. Almost all of them would exceed the tensile strength of the bolt you would twist the bolt on. But torque out is basically just twisting the cinch nut by itself out of the part. So picture a vice grip or a torque procedure. Most of them would have a specific torque that it needs to meet, plus they want to know how much it takes to actually twist it out. And almost every cinch will twist out at some point. So our quality checks would have a specific needed torque out and what does it torque out at. So we have two different numbers that we meet for quality checks. Normally at the beginning and end of a strip coil. But sometimes whenever the quality says, sometimes it's every hour, sometimes It's whatever the quality requires.
I'm not sure if they were asking in that application if we can read it by the tonnage of the press. Not really. The way that you spoke of testing it that way is definitely the most accurate. When it comes to tonnage of the press, there's a lot of variables that can come into that. To know you're getting, you would definitely have a ballpark, but there's a lot of other things happening in the die that can cause tonnage additions or subtractions, that it's hard to monitor that to know that you're getting what you
Okay.
need. If there'd be a massive change in tonnage, of course, you would see that and know that maybe the nuts didn't get work there. That if there was a no nut situation, you would definitely see that. But knowing that it takes, 30 tons to install a clinch nut, that there would be some variables there that I don't know if you would be able to track strictly from your tonnage.
Great questions, everybody.
You have to kind of answer two sides of that question.
Yes, I got you.
Answers.
Thank you.
So we've kind of come to the end of our time period, but I want to thank all of you for joining us. I want to thank all of our fabulous panelists. And finally, to ask each of them for a final message, if they have a final word. Let's start with you, Eckert.
Yeah, first of all, I want to thank you. I want to thank the panel and want to thank to all listeners. My last message is, let's go forward. Let's do more things, put more in the die. Let's make it complicated, because the time is not anymore that you make two simple things. And I'm really looking positive into the future. And we also want to take our part to make it easier for you. And everybody's invited to Chicago.
Fantastic. It seems like you want to say peace on earth, considering your background. Hey, Alas, do you have a final word?
Just again, to echo hard, thank you all today. It was interesting listening to everybody. And, as it comes to inspection, if there's a challenge, we're up for it. So please keep us in mind, and we look forward to seeing you all in Chicago.
Fantastic. David? Here, the beef final word as well. You have a final word?
Yeah, so anybody needs beef, I'm your beef guy.
We all have our orders actually. So
If it smells like cow manure in here, it's probably looking on my beard. I want to say takeaway for a tool shop. Don't look at the way we've always used to do it. Look at the new features. Look at new processes. We have to do this to move forward. And I think the future looks bright for Stanley.
Ryan, you're not allowed to say anything about 3D printing. Other than that, that's me. I know.
Yeah, so I just wanted to, thank PMA for having us out here today. And if you aren't interested in anything more Clinch Solutions, you can go to our website, clinch.solutions. We have a lot of good information there that would kind of compound to what you heard today. Don't be afraid to check us out.
Thank you. Tough.
I'd like to thank PMA as well. Yes, this is great. Chris and Tucker, I want to thank you guys. It's it's hard.
It's a pleasure.
Yeah, it's hard to get. I know you guys are busy, so I really appreciate you coming out, sharing it with us. And same thing, HutchisonTool.com. If you go to die tapping resources, there's the tapping calculator, which unfortunately we had our issues with, but CAD files and other information videos that you can garnish there. And then certainly contact us if you have some applications. We'd love to talk to you.
Fantastic.
I just like to thank the PMA for hosting, and we learned a lot too about other things today. So it's very informative for us, and we appreciate it. It's an honor to be here.
Are you honored enough to invite us to your cabin?
Oh, absolutely.
The Margaritaville beach.
Adam said so.
Tucker, it's so nice to have you here too. Thank you for having us.
Excellent experience, and I think that's all. Manufacturing not being stagnant is what it's all about. Embracing the latest and greatest. Just nice to meet everyone and see that we're all kind of doing the same thing. So,
is this the point where you can do your flip?
Yeah, right.
All right.
Thinking about it.
Sorry. Well, thank you again. And Brad, I think you have the final word.
Yep, thank you. And thanks again to the panel. Lots of great information shared with our audience. So we always appreciate that on behalf of Kate and Lou Crin, our other senior editor. I really thank you for sharing all this great information with our readership. I know PMA really appreciates you guys coming in. Please be sure to join us for our next summer session. That'll be on July 8th. We'll be talking about advanced steel grades and how to stamp them, best practices for stamping high-spec steels. And then on July 22nd, we'll have an automation panel discussion, specifically talking about how to evaluate the use of cobots and robots and hard automation based on your application. So how to kind of pick the right application for your application. So July 8th and then July 22nd. So again, thanks for attending. Thanks for the great questions. Really helped lead to a great conversation. Kate, great job moderating. And thanks everybody, and enjoy the rest of your day.
Thank you. Bye-bye.
Goodbye.